Alright, welcome everybody. So today I'm going to talk to you about how to solve equilibrium problems. Something that I wanted to put in the last video, but I didn't get a chance to were graphs, because that does come up sometimes. And so let me show you what I mean by that. When I talk about a graph, you'll see sometimes in the problems, whether it's in IB or AP chemistry, that they'll have a graph where they do concentration versus time. And then what they'll do is they'll graph concentration versus time for reactants and products. And when they do that, what you'll see is that the reactants will start off where there's a lot of them. So we'll have reactants up here. And the products will start where there's none of them. So the products will start down here. And over time, what happens is the reactants get used up and you'll get the reactants leveling off. The products, those will increase over time, and those will also level off. And the question that they ask is, well, where is there, draw a line where they reach equilibrium? And what you're looking for is you're looking for a spot where they parallel out, where they stop changing. So that would be somewhere, right around here. And this would be my, equilibrium point right there. So these are my reactants, these are my products. Now, it doesn't always have to be where they're like this particular proportion. In this case, the reactants are greater than the products, and so the KEQ would be less than 1. But you could have a situation where the K would be greater than 1, and again, we would have time, and we would have concentration, and we would have our reactants here. And our products, in this case, would go, greater than the reactants. And our products would be up here. And then we would have KEQ is greater than 1. This particular situation is sort of weird, and it throws people for a loop because they always pick equilibrium where the lines intersect with one another. And that's just not true. Like, I'll show you one where they would have a KEQ equal to 1. But in this case, the equilibrium is established, right here. And we could even move that over more because they're still changing. You're gonna let me undo that or not? Okay. So we'd have over here, and so this would be where our equilibrium is established, where the lines start to parallel out. Now imagine if you had a KEQ equal to 1, well, you'd have your reactants coming down here, and then you'd have your products, coming up here, and then they would end up where the lines meet. And in this case, you'd have a KEQ equal to 1. Now, I know on the regions, they say, or you were taught that the equilibrium concentrations of reactants and products cannot or are not equal. It can be, it's just very rare for that to be the case. So there are cases where KEQ is 1, but they use that phrase always. And so they want the idea that the concentrations are constant always, the rates are equal always, but the concentrations are not necessarily equal to each other. All right, so let's get into some of the problems that you might see for equilibrium. And these are math problems that we're doing here. And in this case, they give you a reaction, which I'll highlight up top here. And you can take a second to, if you want, pause the video and read this. And then they tell you stuff about each of the reactants. They say that there is 0.2 moles for 2 liters, and the equation reaches equilibrium when the concentrations of A, or the concentration of A is 0.078. So they give you some starting information, and they give you an ending equilibrium concentration. The first thing that I like to do, and it doesn't really matter which order you go in, but the first thing I like to do is on the side here, I like to write the mass action expression, and I do that over here. I then keep that on the side, and I organize myself in something called an ICE table. And here's my ICE table. ICE stands for initial change in equilibrium. And this has to be done in molarity. So what I'm going to do is I'm going to divide the moles that I'm given divided by the liters. And what they tell me is that the reaction started with A in a 2-liter flask. So they're telling me that this is what I started with. I converted it to molarity, like I circled it. And I don't have any B or C yet because the reaction is just in the initial state. Then I go through the change. And I always put changes in terms of x. So then I'll put the change in terms for A minus 2x, because the coefficient of A is 2, I'll use a 2. B is 1x, and C is 1x. Now notice I have a negative sign for the A, showing that it's decreasing, and a positive sign for the B and C, because those are going to increase, we're going to make that. I then do my equilibrium state, which is my initial plus my change. That's equal to E. My initial for A was 0.1. The change was minus 2x, so I have 0.1 minus 2x. For B, it's 0 plus x, so it's just x. For C, it's 0 plus x, it's just x. Now they told me right here, they told me what A is. And they tell me that A is 0.078 molar. So I know that that is my value for A. That allows me to solve for x. So if I do that on the side here, I solve for x, and I know that x is equal to 0.011. Now what you'll also notice I did was I set Kc up in terms of my x's. But you don't have to do that. So we know that x is 0.011, 0.011, and we know that 2a was 0.078. I can take those values and simply plug them into my Kc and solve for my value and get 0.02. So in that case, I solved for Kc. Here's another problem for you. This one I didn't do for you, and this one you could try on your own, so give this a try and see how you do with this. Again, they want you to solve for Kc. And again, I like to, they want you to find Kp actually and Kc. But something like with this one here, I like to do it in terms of x. Even though I'm told what the equilibrium pressure is, and you can work with that, I find putting it in terms of x makes things easier for me. So please try this problem here, and then we'll get into it and we'll see how you do. Now here's another problem in which they want you to now find the concentrations. They give you Kc. And so this reaction here is where we have a decomposition of HI. So our reaction is 2HI, when I balance it, yields H2 plus I2. It's the same one we did in class. And then I like to fill out my ice table, HI, H2, I2, and put in my values. Well, they tell me that I'm injecting a 2.5 moles of HI into a 10.32 liter container. And so if I take out my calculator and try this out, I have 2.5 divided by 10.32, and I get 0.242 molar of HI. And again, they say that it's into a vessel. They don't tell me anything about H2 and I2. I assume that they're 0 because they are. This is 2HI, so we're going to have minus 2x plus x plus x, x, 0.242 minus 2x. I'm now going to write out my K expression, and they gave me Kc. That is going to be H2, I2, over HI squared. And I'm now going to plug in my values. I know what Kc is. It's 0.00123 equals x times x over 0.242 minus 2x. Now, at first it might look like we're going to have to do some foiling and we're going to have to solve for a quadratic, but honestly, we're not going to have to do that. And the reason why is because this is a perfect square. I can take the square root of everything on here, and if I go ahead and I do that, let me just insert a page here, just insert a page so I can write this out. If I go ahead and I do that, what you'll see is this. If I take the square root of 0.00123, take the square root of that, I get 0.0351. 0.0351 equals x over 0.242 minus 2x. So now I have this set up here. And then when I solve for x, I can do all the math out and I'll get my values for x and I'll plug it back in. So if I do that, if I pause the video now and I go ahead and I do that, let's see what we get for this. So now that you can see I solved for this and didn't bore you with doing it, and what I get is for this is that my x is equal to 0.0079 molar. This allows me to go back to my equation right here and put that in. My I2 value is 0.0079 molar. My H2 value over here is also the same exact thing, 0.0079 molar. And then I can plug it in for this too. If I times 0.0079 times 2, and then I subtract that from 0.242, I get 0.226. And so this concentration right here is 0.226. And so this allows me to find all of the concentrations for these three species. Now this problem was easy in the sense that it was a perfect square. More difficult would be one if I were to have a not perfect square and I'd have to do a quadratic. So what I'd like you to do is I'd like you to try and solve for the concentrations of these equilibrium species, NO, O2, and N2, when you reach equilibrium given this particular problem. And then we can go over that together in class. And what I'll show you is that you'll use the quadratic. Some of you have a quadratic solver. If you don't torture yourself. Go on Google and type in quadratic solver and put in the values and solve for it. And then what I want to show you is a shortcut. Because the AP doesn't expect you to actually solve for quadratic equations, and neither does the IB. And in fact, the value of this KC here makes it possible for us to take a shortcut that I will tell you about in class. All right, thanks so much for watching, and I hope that this was helpful.